Washington, D.C., winter of 1942. Outside, the Potomac River was half frozen, seagulls circling the Capitol dome. Inside the Pentagon, yellow lights burned through the night. An emergency meeting was convened, not to discuss the German forces in Stalingrad, but about a sheet of paper just transferred from Princeton. The header, written in blue ink, read, "Uranium Fission, Military Potential." Beneath it was the curved signature of Albert Einstein. No one in the room spoke. The clock on the wall ticked out seconds longer than any war bulletin. According to the White House Science Advisory Note, January 1942, the memorandum warned that nuclear energy could release heat equivalent to 20,000 tons of TNT from a piece of uranium smaller than a tennis ball. Roosevelt paused as he read. "If Hitler gets this first," an advisor whispered, "the war is over before it begins." It wasn't a voice of fear, but the slow recognition of a man who understood that the sky could collapse without a single bullet being fired. Across the ocean, Stalingrad was burning. Each day, the 9th Army Group reported casualties rising by 5,000. But in Washington, what kept men with stars on their shoulders awake at night lay not on the battlefield, but in a laboratory in Berlin-Dahl, where physicist Werner Heisenberg was calculating fission chain reactions on a blackboard. "The Germans don't need more tanks," the report said. "They need more chalk." A line both cold and terrifyingly true. Since December 1938, the scientific world had been shaken by the discovery of Otto Hahn and Fritz Strassmann. When a neutron struck the uranium nucleus, the energy released was so vast it couldn't be measured by ordinary instruments. At that time, American laboratories still thought it was a strange chemical phenomenon. But the Germans didn't underestimate it. According to the Reich Science Office, 1939, Berlin had formed a secret group under the codename Uran Project. They weren't discussing guns but equations. In his memorandum to the White House, advisor Vannevar Bush wrote, "This is a war of equations, not divisions." In Stalingrad, Soviet soldiers fought in the snow, while in Princeton, Leo Szilard held a piece of chalk and wrote something that made his hand tremble. If each decaying nucleus produced 2 more neutrons, the chain reaction would sustain itself, a perpetual explosion. He had fled Hungary to escape Hitler, but now his idea might help Hitler win. Inside the Oval Office, Roosevelt folded the papers and looked out the window. Winter light reflected on the glass, blending the American flag's shadow with his own image in the mirror. "So this is what fear looks like," he said quietly. An aide noted that line in his journal, later recounting it in a 19511 interview with the Office of Scientific History. When he reread it, he still remembered the hiss of the wind outside the frame and the scent of freshly printed paper, as if history itself had held its breath in that moment. Downstairs, a communications officer tapped out a telegram. "Berlin intensifies nuclear research. Request assessment." The letters struck metal like soft gunfire. The young signalman later recalled after the war that when the paper tape slid out, he saw the phrase Uranium Project and chuckled, "We'll never make a bomb out of rocks." He didn't know that 3 years later, in the New Mexico desert, the ground would shine like the Sunday. Within the American scientific community, the unease spread faster than any news from the front. According to the U.S. War Department memo, February 1942, within just 2 months, over 200 scientists were reassigned from universities to military research. No one knew what they were working on, only that a race had begun and the finish line was a formula. Physicist Robert Oppenheimer later wrote in his diary, "We were not trying to build a bomb. We were trying to stop another one." Oh, the air in Washington was heavy as damp steel. In a War Department meeting room, a world map hung on the wall. Red dots marked German laboratories: Berlin, Leipzig, Hamburg. A colonel pressed a pencil against the Kaiser Wilhelm Institute and said, "That's where our war really is." No one disagreed. Outside, snow slowly melted across the parking lot, sunlight glinting faintly through the window. In that quiet scene, they understood that America's most dangerous enemy at that moment did not wear a helmet, but safety goggles. According to the Military Intelligence Digest, March 1942, reports from Sweden confirmed that Germany had purchased more than 1,200 tons of uranium ore from Belgium. The news arrived on the same day Roosevelt signed the order approving the atomic research program. A clerk later recalled seeing the president holding a black fountain pen, pausing briefly before signing. The pen is still kept in the Smithsonian archives today, its iron casing tarnished, but the signature still sharp. A few hours later, in the room where Einstein once worked, the chair remained where it was, the window slightly open. He had left Princeton the week before, taking a short rest in Long Island. On the desk lay a draft of his letter to Roosevelt, hastily written on library stationery. The last line read, "The release of atomic power has changed everything, except our way of thinking." The evening light shone upon the page, fading the word thinking, and in that silence the fear began to breathe. It wasn't loud, and it had no marching footsteps. It lived in numbers, in equations, and in the small rooms where men tried to control something they never fully understood. That was the moment America realized the real war was not fought in the trenches, but in the limits of human understanding when confronted with the power of the universe. In 1938, at the Kaiser Wilhelm Institute laboratory in Berlin, two chemists, Otto Hahn and Fritz Strassmann, discovered that when a neutron struck a uranium nucleus, the nucleus split and released an enormous amount of energy. They called it Kernspaltung, nuclear fission. According to the German Physical Society record, December 1938, the energy produced by this process was so great that it could boil tons of water in an instant. The discovery transformed the entire foundation of modern physics, but in the hands of a regime like Nazi Germany, it was also something that could change the map of the world. In Berlin, Werner Heisenberg, who had won the Nobel Prize in 1932, was summoned to join the Uranium project. He did not realize he was standing at a turning point in human history. If we can control the chain reaction, we control the war. Heisenberg was quoted as saying in the Reich Science Council minutes, February 1939. Across Europe, the greatest minds Hahn, Heisenberg, von Weizsäcker were all within German territory. In America, many generals had not even heard the word isotope. That disparity was the beginning of a fear spreading slowly across the Atlantic. At that time, American military academies were still bound by classical thinking. The winning weapons were visible ones: bombs, cannons, tanks, things measured by weight, not by equations. According to the U.S. Army Ordnance Review, March 1940, over 90% of research funding was still devoted to developing explosives and artillery. Atomic energy was classified as a theoretical curiosity. A general once asked during a meeting, "How can a reaction you can't even see destroy a city?" The question sounded simple, but captured the full limitations of the era. Meanwhile, in Europe, bombs were falling on London and Paris, but the more terrifying things were happening in underground laboratories. As England, France, and Poland fell one by one, a wave of people began crossing the Atlantic. They carried little luggage but much knowledge. Among them were Leo Szilard, Edward Teller, and Eugene Wigner, men who understood that if Hitler gained control of uranium, the war would end in a flash of white light. In the refugee scientist log, 1940, Wigner recalled that when the ship docked in New York, he looked toward the Manhattan skyline and thought, "Maybe this city will be the first to vanish if we fail." At Princeton, Szilard wrote to Einstein, urging him to send a warning to Roosevelt. Einstein hesitated at first, but after hearing that Germany had stopped exporting uranium from Czechoslovakia, he agreed. The letter, sent on the 2nd of August 1939, was brief and cold. The element uranium may become a new and important source of energy. That was the beginning of a race for survival. According to the U.S. National Archives, 1941, within 2 years of that letter, the United States established the Uranium Advisory Committee, the predecessor of the Manhattan Project. At the same time, fear spread within the intelligence community. According to the British Intelligence Report, 1941, agents in Norway discovered that Germany was stockpiling heavy water, deuterium. a substance essential for maintaining a stable fission reaction. Each liter of heavy water could sustain the chain reaction inside a uranium reactor. When the report reached Washington, the final line read, "If they get 10,000 liters, the game is over." That simple sentence prompted Roosevelt to approve the nuclear project within the same month. However, the difference between America and Germany at that time did not lie in resources but in mindset. While Hitler believed science was a tool of power, Americans still saw it as a tool of research. According to the U.S. Army War College study, 1,942, only 4% of senior officers had basic scientific knowledge. They understood war through maps, not through the periodic table. This made convincing the US government to invest in an invisible weapon, a second war, a war between those who understood energy and those who believed in gunpowder. At Los Alamos later, Robert Oppenheimer told Groves, "Our enemy isn't the German army, it's time." That statement captured the central conflict. The race was no longer about who was stronger, but about who understood physics faster. In a world stretched between visible and invisible battles, Heisenberg's equations became weapons more terrifying than the Panzer. A report from the US War Department brief, June 1942, stated, "Germany may have the scientists, but we must have the courage to believe ours." The phrase was underlined 3 times. From then on, every technical decision, every reactor design, every uranium molecule was regarded as a piece in the race of intellect. In the meeting rooms of Washington, maps of Europe were pinned to the walls alongside blurred photos of Hahn, Heisenberg, and Meitner. One officer later recalled that whenever he looked at Heisenberg's picture, he did not see a scientist but a bomb counting down. The war in Europe continued with gunfire, but in laboratories on both sides of the Atlantic, another war had begun, the war of knowledge. And for the first time in history, fear had a formula. Before moving to the next part, if this story resonates with you, please like and share it so more people can see. Leave your thoughts in the comments. Your words will be the motivation for us to create even more great videos. In the autumn of 1942, at the height of World War II's intensity, the U.S. War Department appointed a new engineering general as director of the Manhattan Project, the name MAJ. General Leslie Richard Groves appeared in War Department Order, number 2804, September 1942. Many in the military were surprised. He was neither a scientist nor a strategist. Groves was famous for completing massive constructions on time and under budget, such as the Pentagon, finished in 16 months for $83 million USD, a feat for its time. People said he could run a storm without spilling his coffee. Groves entered his new Washington office without a greeting. He placed a 300-page file on the desk and quietly said, "We'll need to build a weapon before they build faith." One officer later recalled that his voice sounded like he was reading a death sentence for time itself. According to the Army Corps of Engineers memoir, 1947, Groves spoke in a tone that was both dry and precise, every sentence an order. He did not believe in inspiration, only in discipline and deadlines. Throughout his career, Groves pursued order within chaos. Born in 1,896 inches Albany, New York, the son of a minister, he was raised in an environment that regarded labor as faith. Upon graduating from the U.S. Military Academy at West Point, he ranked 4th out of 103 with near-perfect technical scores. In Panama, he had once built a bridge in the tropical jungle using only a single sketch. For Groves, construction was a symbol of control, and chaos was the enemy to be subdued. According to the Manhattan District Administrative Log, October 1942, when assigned to lead the nuclear project, he demanded 2 things: absolute authority and absolute secrecy. No reports to Congress, no leaks to the press. He understood that what they were about to do would transcend the boundaries of war. One of his first notes, written in red ink, read, "If Hitler has 6 more months, the world will end in darkness." He later repeated this line at the project's first meeting with engineers in Washington. It was not a declaration, it was a compass. Groves was known for his ability to turn theory into tangible achievement. According to Colonel Kenneth D. Nichols, his deputy, Groves didn't care how an atom split, only how fast we could build the plant that made it happen. When he arrived in Oak Ridge, Tennessee, a land still covered in farms and woods, he simply said, "We'll need a city here, and we'll build it before winter." 6 months later, over 59,000 people lived and worked there. According to the U.S. construction record, 1,943. For Groves, building was fighting. But he could not do it alone. Groves needed someone who understood the language of atoms, someone who could speak to the brilliant minds he could not control through rank. That man was Robert Oppenheimer, a physics professor at the University of California, Berkeley. At their first meeting, Oppenheimer wore a frayed jacket and shyly spoke about quantum mechanics. Groves looked at him and noted in his report, "Thin, unmilitary, brilliant beyond tolerance." 1 week later, he appointed Oppenheimer as the project's scientific director. According to the Manhattan Project Personnel Memo, November 1942, Groves chose Oppenheimer not for his fame, but for his ability to connect people. He said, "The bomb isn't built by machines, it's built by minds." That statement became the foundation of a new working model, physicists, chemists, engineers, and soldiers united by a single objective. Oppenheimer later recalled, "Groves was a paradox. He distrusted scientists, yet he trusted me absolutely." In meetings, Groves always sat at the head of the table, listening silently. When physicists argued, he would simply ask, "How long and how much?" He didn't need to understand the equations to sense their weight. In those early Washington days, Groves faced skepticism from every direction. According to the War Production Board report, 1942, many officials believed, "The project is an academic indulgence." A congressman asked bluntly, "Can an explosion come from mathematics?" Groves replied coldly, "It already has." He understood that to win, one must first turn doubt into fear, the only fuel powerful enough to move a government. Groves called his team the Army of Brains. He gathered the greatest names: Enrico Fermi, who built the first nuclear reactor beneath Stagg Field, Chicago; Ernest Lawrence, father of the cyclotron; Arthur Compton, expert in quantum physics; and hundreds of refugee scientists from Europe. According to the University of Chicago record, December 1942, Fermi's experiment proved that a nuclear chain reaction could sustain itself, the first step in turning theory into reality. Groves looked at that result and knew he held something that could shape the world. But he also understood that an idea, if left unchecked, could destroy its creator. Each time he signed a report, he added one line at the bottom: "Control is our salvation." That line became the creed of the entire project. By late 1943, as the Manhattan Project expanded across 3 states, Groves often worked until 2 a.m. One officer once saw him standing alone before the Hanford plant model, the light reflecting off his sweat-soaked face. He said nothing, merely touched the cold metal structure before turning away. A soldier later wrote in his journal, "He looked at it like a father looking at something he can't protect." Leslie Groves never kept a diary and left behind no memoirs. But in every telegram, every memorandum, one truth was clear. He did not fear failure. He feared being too late. And in that fear, a project was born not to kill, but to prevent another from killing first. And somewhere in that relentless precision, war itself began to change shape. When Leslie Groves said he needed a city, he meant it. The Manhattan Project was not a small laboratory, but a chain of massive industrial complexes, linked together by secrecy and precision. 3 centers formed the core of this network, each holding a distinct and irreplaceable function. Oak Ridge was responsible for uranium separation, Hanford for plutonium production, and Los Alamos for weapon design. These sites did not appear on civilian maps, but in 1943 and 1944 they became the largest and most secret factories in the United States. At Oak Ridge, engineers erected rows of copper-separating machines as long as factories. The devices, called calutrons, operated on the principle of electromagnetic separation, with engineers adjusting magnetic fields to isolate the isotope U-235 from U-238. The level of precision required was terrifying. One minor error could ruin the entire cycle. Thus, people spoke of manipulating at the level of 1 part per billion if necessary. The Colutrans ran day and night, operated by workers, technicians, students, and women in the plant, all laboring under immense pressure, with roaring ventilation fans and hot metal beneath their feet. Oak Ridge's achievement was the extraction of uranium for the next phase of the process, gram by gram, with time and effort equivalent to a monumental act of production. At Hanford, the work took a different direction, not isotope separation, but plutonium creation from uranium. There, graphite reactors were designed to guide neutrons and sustain a controlled chain reaction. Afterward, the material was cooled and transferred to chemical processing plants to extract plutonium from the fuel rods. Operating a reactor at that time was like walking a tightrope. Thermal, neutron, and heat transfer calculations had to be exact to the last digit. A single reactor consumed vast amounts of energy, and the entire Hanford complex required as much electricity as a small city. In return, it produced new material for weapons, accumulating each day a small portion of something capable of altering the course of the war. Los Alamos was where theory took form, where physicists and engineers assembled every detail of the weapon. There, Robert Oppenheimer coordinated a team of specialists from mathematicians to machinists shaping molds. Weapon design required not only understanding chain reactions but also deep knowledge of explosives, materials, and precision mechanics. The structure of the explosion and the arrangement of the explosives around the radioactive core, the methods for assessing stability, all were tested, modeled, and calculated step by step. Small prototypes, controlled scale tests, and thousands of measurements were recorded in notebooks so that every bolt and every valve would perform in perfect synchronization. Two main technological directions led to success. The first was electromagnetic separation, with calutrons adjusted to achieve a precision described by engineers as 1 part per billion to obtain sufficiently pure U-235 for the weapon core. The second was plutonium generation through graphite reactors, a parallel but independent path that created plutonium within uranium cores bombarded by neutrons, later separated through chemical methods. These two technologies stood like twin rivers flowing toward the same sea, each with its advantages and drawbacks, yet both demanding immense resources to sustain. The magnitude of scale was reflected in the numbers. The entire project mobilized around 130,000 workers, according to wartime administrative records, ranging from engineers to medical staff, from construction workers to logistics managers. The total cost, calculated at the end of the war, exceeded $2 billion in 1945 currency, a figure that made all peacetime budgets pale in comparison. The operation of the plants represented a colossal energy load, consuming about 5% of the nation's total electricity supply, a capacity that had to be maintained while the civilian economy continued to function. All of this effort was to produce the first materials. Each reactor, each production line, each laboratory yielded about 6 grams of plutonium per day, a quantity small enough to fill a spoon, yet containing energy capable of changing history. Technical details turned into tangible results. Once all components were assembled, the production process from ore to weapon core operated like a vast assembly line. Materials passed through various stages: isotope separation, smelting, reaction, and chemical extraction, each step requiring strict control and maximum secrecy. Blueprints, calculations, and experiments were stored in secure archives, with access restricted to only a few individuals. The application of all these achievements was not a distant expectation but a strategic instrument in the hands of decision-makers. As the plants operated, engineers and technicians worked in an environment that was both experimental and industrial. They lived in newly built towns, slept beside circuit boards, and ate in canteens where conversations quickly turned to numbers and measurements. A female technician later recalled that when she saw the first separation results, she felt an almost sacred fear, for she knew she had just witnessed something humanity had never seen before. For the first time in history, humanity built a machine capable of recreating the energy of the atom, a machine not confined to a small laboratory, but on an industrial scale, set amid forests and deserts, operated by human hands and data. From uranium crystals to the weapon core, every step was calculated and measured, grounded in ambition and precision. In this new world, technology was no longer an invention, it was a manufactured power. Jornada del Muerto Desert, New Mexico, early morning of the 16th of July 1945. The entire land, whose name literally means Journey of the Dead Man, lay still beneath a haze of dust. Wind swept across the low mountain ranges, carrying the scent of metal and the dry heat of summer. Atop a 30-meter steel tower, a 4.6-ton metal sphere, known to the engineers simply as the Gadget, waited to do what no one had ever dared attempt. According to the U.S. Army Test Command log, July 1945, 425 people were present within a 16-kilometer radius, each one knowing that if the calculations were off by even 1,000th, the desert would vanish from the map. Leslie Groves had been on site since 2 a.m., walking slowly along the control tent. He said nothing, asking only one word. Weather? An engineer replied, wind stable, light to the east. Groves nodded, his face expressionless. A few miles away, Robert Oppenheimer stood inside a concrete bunker, eyes fixed on the horizon. According to the Los Alamos Journal entry, July 1945, he had stayed awake for 3 nights straight, fine-tuning the final parameters of the detonation system. On the table beside him, a cup of coffee had gone cold, the steam dissolving in the dim light of an oil lamp. At 5 hours, 29 minutes and 45 seconds a.m., the signal was sent. A flash erupted so bright that people 16 kilometers away felt the light pierce through their closed eyelids. The temperature at the explosion's core exceeded 10 million degrees Celsius, equivalent to the sun's core. According to the U.S. Geological Survey report 1946, the blast created a fireball 600 meters in diameter, and the shockwave shattered windows in San Antonio, 190 kilometers away. The ground melted, crystallizing into a grey-green glass called trinitite that stretched 1,100 meters around ground zero. One observer recalled, "The light was so bright, I saw my bones through my hands. It was a moment no one would forget, both surreal and absolute." Groves stood still, sweat tracing down his collar despite the cold dawn air. He neither cheered nor applauded, only stared at the dissolving glow. In those few seconds, the greatest industrial war effort in human history was contained within a single flash of light. In the bunker, Oppenheimer quietly recited a verse from the Bhagavad Gita. "Now I am become death, the destroyer of worlds." Those near him couldn't hear clearly, but later they said his eyes looked as if he had seen something no man should ever see. Another engineer, Kenneth Bainbridge, turned to him and murmured, "Now we are all sons of bitches." The silence that followed was as heavy as the drifting ash outside. According to the Army Medical Observation Record 1945, 20 minutes after the explosion, radiation levels at ground zero were 1,200 times above safety limits, and radioactive dust spread as far as Texas. A team of scientists in protective suits entered the zone, measuring soil samples and collecting fragments of metal so hot they had to use steel tongs. In archival footage, they can be seen bending down to pick up a still-smoking shard of glass, then looking up at the empty sky, where the massive mushroom cloud still coiled. From the bunker, Groves signaled for the jeeps to move toward the test site. When he stepped out, he looked around. The desert was now a shimmering grey surface, as if coated with a colossal mirror. According to the account of Officer Harold Bush, Groves said quietly, "This is what the end of time would look like." In the first sunlight of the day, droplets of molten glass glowed green, yellow, and violet, a scene both beautiful and terrifying. That same day, a brief report was sent to Washington, containing only 2 lines. Test successful. Yield higher than predicted. No figures, no descriptions, just two statements, yet they were enough to change how humanity perceived its own power. Roosevelt had died in April, and President Harry S. Truman read the report aboard the train to Potsdam. He remained silent, then said to his aide, "We have unleashed a force too big for men to govern." In the hours that followed, at Los Alamos, the scientists began to laugh and cry at the same time. Some embraced, others quietly walked away. According to the Los Alamos Oral History, 1947, Oppenheimer left the room and walked along the fence, where the morning light spread across the desert. A young student captured a photograph of him with his head bowed, hands in his pockets, dust swirling around. That photograph later became an emblem of the moment when humanity touched the boundary between knowledge and morality. That morning, the New Mexico sky cleared again, and the wind swept across the land that had just been scorched. A young soldier, not fully understanding what he had witnessed, wrote in a letter to his mother, "It looked like sunrise, but from hell." Simple words, but terrifyingly precise. Trinity was not merely a weapon test, it was a test of faith, of ethics, and of intellect. They had brought the light of the stars to Earth, and when that light faded, none of them saw the world the same way again. The desert was silent, but in that silence, humanity had crossed the threshold of the universe. Only 3 weeks after the Trinity test, the power of the atom was brought to the battlefield. On the 6th of August 1945, the B-29 aircraft Enola Gay departed Tinian Island at 2:45 a.m., carrying the 4,400 kilograms uranium bomb Little Boy with a yield of 15 kilotons. According to the mission log of the 509th Composite Group, August 1945, the target was identified as the city of Hiroshima, Japan's military and industrial center. At 8:15 a.m., the bomb bay doors opened, and within 43 seconds, a light 10 times brighter than the sun exploded in the sky. The temperature at ground zero reached 3,000 degrees Celsius. The earth melted, buildings within a 2 kilometers radius were obliterated, and in an instant, 70,000 people vanished from the surface of the earth. According to the U.S. Strategic Bombing Survey 1946, more than 69% of Hiroshima's structures were destroyed. In that scene, the human shadow imprinted on the concrete stairway wall of the Sumitomo Bank became the grim symbol of a new era. A pilot aboard Enola Gay recalled, "The city was there 1 minute, and the next it was gone." No one said another word for the rest of the flight back. 3 days later, on the 9th of August 1945, the second bomb, a plutonium device named Fat Man, was dropped on Nagasaki. Its yield was 21 kilotons, equivalent to 21,000 tons of TNT. The city was chosen because of the bad weather over the original target, Kokura, according to the U.S. Army Air Force's After Action Report, 1945. The explosion created a 3.2 kilometers radius of destruction, killing more than 40,000 people instantly. By the end of the year, total casualties in the two cities exceeded 200,000, the majority of them civilians. On the 15th of August 1945, Japan announced its unconditional surrender. Radio Tokyo broadcast the weary voice of Emperor Hirohito. "The enemy has begun to employ a new and most cruel bomb. After 2,194 days of war, the world entered an era in which victory was no longer measured by divisions or battleships, but by physical equations. The immediate impact was a global shock. Military leaders and heads of state realized that this weapon not only ended a war, but also redefined the concept of power. According to the U.S. War Department Bulletin, September 1945, the United States had spent over $2 billion developing the atomic bomb, but in doing so had saved millions of lives compared to an invasion of Japan. Yet soon afterward, during international conferences, silence filled the room each time the word atomic was spoken. Journalist William Lawrence of the New York Times, the only reporter permitted to witness the Trinity test, wrote, "We have crossed a bridge that cannot be uncrossed." Oh, strategically, The United States had not merely won a war, it had gained the right to define the global order. When President Harry S. Truman attended the Potsdam Conference in late July, he knew he held in his hands the greatest power humanity had ever possessed. His advisers called it deterrence by existence, a weapon that never needed to be used again, for its mere existence was enough to make enemies yield. But that very existence immediately opened a new era of competition. According to the Soviet Atomic Report, 1949, only 4 years after Hiroshima, the Soviet Union successfully tested its first atomic bomb at Semipalatinsk, ending America's nuclear monopoly. The ideological conflict between the two superpowers became a technological race, where every gram of uranium and every megaton of energy became the measure of political power. From this emerged the concept of mutual assured destruction, MAD. If one side attacked, both would be annihilated. In the 2 decades following the war, more than 60,000 nuclear warheads were built across the globe, from Nevada to Siberia, from the Nevada test site to Novaya Zemlya, according to the UN. Atomic Energy Report, 1965, the total yield of the world's nuclear arsenal reached a level capable of destroying Earth more than 20 times over. What Oppenheimer and Groves once saw as a proof of principle had now become the strategic mechanism governing the planet. Trinity had been an experiment of intellect, but Hiroshima was the proof of consequence. Groves wrote in his 1946 report, "We built it to prevent tyranny, but now we must prevent ourselves." Within that sentence lay the recognition that a technical victory could turn into a moral burden. Scientists who had worked on the project, such as Leo Szilard and James Franck, later submitted petitions opposing further bomb production. They understood that knowledge had escaped the hands of its creators. The post-war world no longer believed in the strength of armies, but in the strength of managed knowledge. From 1945 to 1949, the United States increased its nuclear research budget by 600%, leading to the establishment of the Atomic Energy Commission, AEC, an institution overseeing not only bombs but also the ethics of science. During hearings, Oppenheimer was asked, "Do you feel guilt?" He replied, "I feel knowledge." The race against Hitler had ended in victory, but it opened another longer and more solemn race against ourselves. Humanity had proven capable of creating the energy of the stars, yet in doing so had placed itself within the peril of its own intellect. When the light of Hiroshima faded, a new darkness began to descend upon humankind, and from that day on, every sunrise carried the memory of that fire. After the victory, the silence lasted longer than the explosion. In 1954, 10 years after Trinity, Robert Oppenheimer sat in a hearing room of the Atomic Energy Commission beneath harsh white lights and the steady hum of a recording machine. The inquiry lasted 4 weeks, involved more than 40 witnesses, and ended with a political verdict. He was stripped of his security clearance. According to the U.S. Atomic Energy Commission hearing transcript 1954, the indictment was not about science, but about faith. While waiting for the decision, Oppenheimer looked down at his trembling hands. "The physicists have known sin," he said, as if confessing for an entire generation. When he left the courtroom, a reporter asked if he felt regret. Oppenheimer replied briefly, "I don't regret the work, only the world it made." That sentence closed a chapter of American science, where genius became the symbol of solitude. He lived reclusively in Princeton, teaching and writing, sometimes walking along the Long Island shore where the wind pressed against his worn coat. A student recalled in the Princeton Oral History 1966, "He never raised his voice, but you felt he was talking to ghosts." While Oppenheimer bore the weight of moral judgment, Leslie R. Groves faced another burden, the burden of victory. He was awarded the Distinguished Service Medal, appeared at Pentagon ceremonies, yet his face rarely showed a smile. According to the Army Corps of Engineers memoir, 1958, Groves once said in an interview, "I never saw victory. I only saw that we were on time." The remark captured his essence, a man who measured war not by triumphs, but by schedules. Groves retired in 1948, living quietly in Virginia, far from the press. A neighbor recalled that every morning he would sit on his porch reading the newspaper, always folding it at the page about nuclear tests. He never commented, only furrowed his brow. When he died in 1970, the only photograph on his desk was one taken at the Trinity Desert, a faint glow in the distant darkness. Across the Atlantic, the mines that had once terrified America were brought over under Operation Paperclip. According to the U.S. War Department Archive, 1,946, more than 1,600 German scientists, many of whom had served the Nazi regime, were transferred to the United States. They worked at Fort Bliss, White Sands, and later at NASA. History's paradox had come full circle. Those once branded as threats to civilization now helped send humanity to the moon. An American engineer wrote in his memoir, "We feared their minds, then hired their hands." As the world slowly recovered from war, the creators of the atomic bomb carried a loneliness no one else could share. Some continued researching civilian energy. Others chose silence. Physicist Leo Szilard, who had written the letter warning Roosevelt, turned to biology and said, "I've spent my life preventing what I helped begin." In the 1960 seconds, Oppenheimer received the Enrico Fermi Award from President Lyndon B. Johnson. He stood in the hall, applauding alongside those who had once doubted him, then walked away in silence. The last image left of him was turning back with a weary smile. Both sides of that war, the United States and Germany, learned the same lesson. Intelligence is not innocent, and science can never be separated from its consequences. Those who created the light of the stars had realized that within that light, there also lay the shadow of themselves. World War II ended in light, but that light did not fade with the sound of gunfire. The explosion over Hiroshima did not merely erase a city, it opened an era in which fear became technology, and knowledge was measured by its capacity for destruction. According to the U.S. Atomic Energy Commission Bulletin 1946, after the war ended, over 90% of America's defense scientific research shifted toward applications of nuclear energy. In that same year, the world understood that peace was no longer the silence of victory, but a fragile balance between knowledge and power. Amid the newly built government buildings in Washington, the Statue of Victory still stood, but those who had created the atomic bomb knew they had not truly won. Groves once said, "We did it before the enemy did, that's all." That dry statement contained the entire essence of the age. There were no mighty powers, only faster ones. When the first lights of the Hanford plant went dark, another world lit up the world of control, deterrence, and legitimized fear. Throughout the decade following the war, nations built thousands of nuclear warheads and called it peace. According to the United Nations Disarmament Report, 1960, the United States and the Soviet Union alone possessed over 30,000 nuclear weapons. Humanity had created technology capable of reaching the stars, yet turned it back upon the Earth itself. The question never disappeared. Had we truly learned anything from war? If Hitler had 6 more months, would history still be written by the victors? That question is not a hypothesis, but a reminder of the fragile boundary between civilization and annihilation. When Oppenheimer watched the Trinity explosion and said, "Now I am become death," he was not prophesying. He was foreseeing a future where knowledge would no longer be harmless. An engineer at Los Alamos later wrote in his journal, "We built a weapon to save the world, and in doing so, we made a world that needed saving." In war museums today, grey-green trinitite fragments are still displayed behind glass. Under the lights, they shimmer like gemstones, but each sparkle is a frozen memory of energy that once scorched the sky. A tour guide told a visitor, "It's beautiful, isn't it?" And that's the problem. That sentence captures humanity's greatest paradox. The most beautiful thing ever created is also the most terrifying. Nuclear technology has illuminated cities, powered hospitals, and propelled probes beyond the solar system. Yet it has also left millions of tons of radioactive waste buried in the earth. Every technical advance carries a moral question. From Trinity to Chernobyl, from Hiroshima to Fukushima, humanity is still learning how to live with the very power it once feared. If this story makes you believe that intellect can both save and destroy the world, share your thoughts. History does not exist to glorify victory, but to remind us of its price. Every time we read the names Oppenheimer, Groves, Hahn, or Heisenberg, we do not only see genius, we see reflections of ourselves, living in the era built from their aftermath. When the light of Trinity flashed, humanity proved it could grasp the energy of the stars. But as that light dimmed, it also realized it was not ready for it. A single split atom ended a war, and at the same time, forever divided mankind's faith in itself. From that day on, every dawn has carried the memory of that fire, and the question still echoes across peaceful cities. Are we keeping peace, or merely keeping the fire waiting to rise again? Have you ever lived through days of war that fierce? Sleepless nights, the sound of sirens, empty streets, and a glow on the horizon. Those memories may have faded, but the fear, the faith, and the courage remain within us still. If this story made you think of a time long past or touched something within you, support us with a follow and leave a comment about what you or your loved ones experienced during the war. Every shared story, every memory, is a part of history preserved. We hope that stories like this will never be forgotten. And perhaps, one small thing from you is enough to let the light of that memory continue to shine.